All right. So let's start from the practice. No, let's start from the actual exam from no. Yeah, let's start from the practice exam. So this is practice exam fall 2019, exam 3. So, um just going through it, like starting again at the first page, first question, he asks you about the relationship between all the different molecules shown, and then you have to say whether they're diastereomers, enantiomers, or identical. And just as a quick recap, diastereomers are where not all of them have changed. And then enantiomers is where all have changed. And is identical is basically none have changed. And when we talk about this, when we say like them, or like when we say not all of them have changed, what we're talking about is the chirocarbons, and they can switch back and forth between R and S. So if all of them, if all the chirocarbons have switched from R to S or from S to R, then that's called an enantiomer. If one of them might have stayed the same but the rest of them switched, then that's a diastereomer. Identical is where everything is exactly the same as it was before. And so we've already talked about different ways to identify identicals, because sometimes identical molecules can look like enantiomers, but it's just the same thing, but you're viewing it from the other side. So an example of that would be something like this, and I'm using the same molecule that he has here initially. But I mean, there's going to be something coming off this way and something like that, right? And I'm not really going to go into, because I don't want to figure out how to, do this. But oh wait, so I'll just go ahead and do it. So let's say there was a BR on both of these sides, and then um there was, and I'm taking this straight from your thing. So let's say we were dealing with these, basically. Um, what happens is that if you do R and S, you're gonna find that this is S, this is R, this is R, and this is S. So you might think to yourself, well, everything has switched. This one right here was an R, now it's an S. This one over here is an S, now it's an R. So everything has switched from R to S or from S to R. So that's perfect. So you might say enantiomers. But what we learned is that since there's a plane of symmetry, this is just the same molecule, but you're viewing it from behind. And so who's to say that this chirocarbon here that I'm drawing in green isn't also this one right here? And this one that I'm going to do in red is this one right here. Therefore, the R stayed the same. So it went from R to R, so that's the same, and S to S. So both of them stayed exactly the same. And therefore it is identical, right? Do you have any questions about this? And this is only for things with a plane of symmetry. Now, if there wasn't a plane of symmetry, and I'll give an example if that works perfectly, let's do the exact same thing. So in this case, we're starting off with the same thing, but let's just add a little, actually I want to change this a little bit. Um, let's make it a cyclohexane. And I'm gonna add a methyl here. Nope, that's still plane of symmetry. Double bond here. Okay, so let's do R and S. So for the one on the left, this is 1, this is 2, this is 3. So this is going counterclockwise. So again, going counterclockwise with a forward hydrogen is going to be an S. And then let's do the one on the right. So for the one on the right, Br is 1, this is actually 2, this is 3. So this is going in a counterclockwise direction again, but this time, and also the hydrogen is forward, is backwards, so it's an S, right? So this was S and S. Now let's draw something similar to that. Um, so when you do R and S for these, so this is 1, 2, 3, so that's going counterclockwise, forward hydrogen, it's an R, right? And then do the other one. This is 1, 2, 3. So this is counterclockwise, and this is also an R. So you might be like, this is the same. This almost looks like the same situation above. So in the above situation, we went from S and R to R and S, and so you might think that they're enantiomers, right? But they're actually identical because the one that I did in green right here is the same one as this one, and they're both S. And the one I did in R is the one that's red is R in both situations. So it's the same thing. Nothing has changed about it. But in this bottom one, we know for sure that this carbon right here definitely went to R. It definitely went from S to R because there is a differentiating factor here. This chiral carbon on the right of the molecule is very close to the double bond. And so we definitely know for sure that those are the two same carbons and they switched from S to R. And similarly with the one on the left, the cryocarbon on the left of the molecule, it switched over here from S to R. So these are enantiomers. So just as an overview again, the only time you have to look out for this kind of thing is when there's a plane of symmetry like that. Because then it might look like enantiomers, but actually they're just identical. So that was kind of one of the catches in this first question there. Moving on to the second one, he asks you about some more like relationships. And one thing I would say is for this list where he says identical, constitutional, enantiomer, diastereomers, look out for a constitutional one. Just don't throw that off the table. Like the fact that he put it there in the list, pay attention to that and look for some constitutional isomers. The first thing you should do when you look at these molecules is see if they're even a constitutional isomers. Then move on to examine your chiral carbons and see how they change. Okay. So again, these first two questions are about relationships between molecules. We'll see later that you can, within an individual molecule, they can be classified as chiral, achiral, or meso. So then this third question right here is find which of the following cannot act as a nucleophile. And again, the first thing I like to do for this, and by now you've recognized BF3 because we talked about it so much, how BF3 doesn't have any lone pairs. So the first thing you need to do is look for something that has lone pairs. It cannot act as a nucleophile if it doesn't have lone pairs. So all those other molecules in question 3 have lone pairs except for BF3. So all of them can act as nucleophiles, but some of them are going to be better nucleophiles than others. Question number 4, he says to assign R and S. And so this one is like a little bit, it's a little bit tricky because, again, it's just with the numbering like that gets people sometimes. There's some very tricky ones that he can do where it's hard to tell like how to count it. But let's do B because I think that looks a little more tricky. So there's a carbon, CH3 2, and then okay. So when you're looking at this and you need to go number it, which I'll do in green. First of all, if you look at our first molecules for each side, they're all carbons. This means that since they're all carbons, you're going to need to examine the things that carbon is attached to, right? And you'll notice that this carbon, the one right here, is attached to a nitrogen 3 times. So if we write it out, it'll be C, N, 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 right? And this other carbon on the left is attached to a carbon 3 times. So C, 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 C. And the one on the top is only attached to 2 carbons. So it's C, 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 H, because it is attached to 1 hydrogen as well. So from here, that's information for us to go off of that and start numbering them. So this one is attached to nitrogens. Nitrogens are much heavier than carbons. So this is going to get number 1. And then you do this, it's going to be back. So that's R. Okay, so then this next one is something that you guys will definitely get. So I want someone to walk through this actually. Who wants to do this one? Um, let's see. Destiny, you want to do this?
Yeah, I can do it.
Oh, guys, was I cutting out for anyone else?
It was cutting out a little bit, yeah.
Oh, that's weird. Okay. Oh. All right. Let me know if it happens again. Okay. C, D. Okay, and then okay. Why don't you tell me how to work through this, figure out what all these products are? And the question is, you have to figure out what A, B, C, and D are. So how do I start this problem?
Okay, so I first start by like taking the product that we get from B and D, and I do like kind of like a root A, root B thing, like where I split on each side of the oxygen.
Mm-hmm.
Um, yeah, and then I basically write it out. So for like root A, it would just be like you write the beginning part, and then you put like a BR on it. Yep, and then you would keep the F, like plus the O. You hear me? I can't tell if it's frozen. Oh, okay.
Yeah. Yeah. No, no.
Um, so after you do the O and you look at like the blue sheet,
Mm-hmm.
and then you get like a secondary, like the BR is attached to secondary, so you would get an
Yeah.
E2 reaction.
E2. Okay. So that would mean elimination. So it would be like this, and it would just eliminate there. A double bond.
Yeah. Yep. So then we can't really use that one. So then we'd go to B, and then that would just be like the opposite. So like the O would stay attached to the first part, and then the BR would be on the other part.
Okay. And what does
Then
that give us?
that would give us SN2. So then it would just be like our beginning product that we basically got from B and D.
Okay. Cool. So what does this mean?
Like you want to use the C and D because I think you forgot to write it, but the reactant is HBr, BR. So that's how we know it goes like with D. We're going to look at the SN2 reactants. So the one with the Br is the product for D because we see like the HBr, so that's how we know.
Mm-hmm.
And then the one with the O minus would be for B. And then you kind of, since he wrote in like the instructions, he said that like compounds A and C are alcohols, so you just add an OH instead for like A and C, but with the same like lines, I guess you could say.
Okay. So, since we know that D is the one with the Br on it, D is gonna look like this, right? And so all we have to do is draw the same thing but with an alcohol right before it, like this. And then we know that product B is the one that must be the one with the O minus. So it looks like this. So we know that it must have started out like this. Oh, no, no, no. Like this. And also we should put our Na plus here, right there. So our answers are B is this, D is this, C is this, A is this. Okay. That question will probably be on your final because he puts that question in like every single exam and stuff. Or something similar. Um, okay. So after that, he has some definitions, and again, like I'd recommend to look at those and see what he's like what that person said because they got full points, and it's important to like word it or like explain things the way that he likes. Usually, you don't want to explain it with words. Just a second. Guys, just a second. Right. Sorry for the interruptions. It's okay. So, yeah. So after that, he asks about cyclicization. So he will always say the word cyclicization if you're supposed to cyclize something. So in this case, this is question 9 on page 2 of the practice exam 3. So basically, the way that he did it in a condensed formula, you should probably just always switch that to a bond line structure because you can't really, he's not expecting you to draw your final product in condensed formula. So if you draw it in your bond line structure, it's gonna look something like this. And since he said it's cyclicization, and he has an NaH here, you know that it's gonna be probably the O attacking this, right? And so basically, all you have to do is kind of like count up your carbons, make sure you have, like, you know how many carbons there are, and you can draw those carbons out, right? And carbon number 1 is attached to an OH. Carbon number 3 is attached to a Br. And we know again that this is attacking here, and this is pronating. So when you just go up and draw your answer, it's going to look like this. And that's it. And make sure you don't include your hydrogen here. Your hydrogen actually leaves, probably like in the first step actually. Um, one of the first steps is that this H minus is going to attack your hydrogen so that the O is negatively charged. And then it's kind of has that need to attack your beta carbon. Or I'm not sure if it's that way or if it's afterwards you have this intermediate thing right here. I've seen it done both ways in people's mechanisms and like this, whether it happens afterwards. Actually, I think it's better to go with the afterwards one. So the hydrogen comes along after the cyclicization has happened and takes away that extra hydrogen. And if he asks for a mechanism for your cyclicization, you must include this section right here because people leave it out and you'll get points off if you don't put it there. Next, he has this one. It's a chair conformation, and we talked about how OTS works, right? So, well, I guess in this case it really isn't OTS, or it's more the other one. Uh, we don't have an acronym for it, I think, but it's the one that's OS and then has CF3 at the end. It's a very, very good leaving group. So, when you see this thing, all you have to know for sure is that this is a good leaving group, and it leaves before the oxygen. So that means everything, including the oxygen, breaks off. All right, everything, including the oxygen, breaks off. That's really important. So the oxygen is no longer there. And what happens is that since this is reacting with NaN3, the N3 comes along and can attack that beta carbon. And so that's going to make it go like this. It's going to be going straight up though. Because with SN2 reactions, because it is SN2, it's a secondary leaving group with a very good, strong nucleophile. So since this is SN2, since it's SN2, um, everything is going to happen at the same time. Both the pronation of the good leaving group and the attack of the nucleophile are going to happen at the same time. So that means that the nucleophile has to attack from the other side. So it goes from R to S or from S to R. So in the beginning, this would be 1, this would be 2, this would be 3. So that's going in a counterclockwise direction. And the hydrogen is, what is it? Julie. Wait, is Julie here? Ollie, what direction is the hydrogen? Is it forward or backwards?
And this one for the arrow.
No, for the we're doing R and S for this carbon.
Oh, okay. It's up, right?
It's up, yeah, because the hydrogen is going up this way. And so since hydrogen is forward, which is the other way of saying up, um, we know that if it's going counterclockwise and the hydrogen is forward, then that is R, right? So this went from R to, and then we need to make sure it's S in this situation. So this is 1, this is 2, this is 3. So this is again going counterclockwise, but this time our hydrogen is down. So it is S. All right. So just again with SN2, you have to make sure to tap the opposite side. All right. So okay, so this question is something that's really important. So he says that he gives you this is question 11, practice exam. So he gives you 3 different things, and I'm gonna write them out in bond line structure here to make it easier to understand. And so there's this structure, and this structure. And so we have to rank them from most to least nucleophilic. Um, and so, as we know from our trends with nucleophilicity, it goes like in this direction right here. And so, something like sulfur is going to be more nucleophilic because it's farther down. O is usually here, and then S is right underneath. So, since S is farther down in the nucleophility chart, we're going to put the one with sulfur first. So, that's going to go from the most nucleophilic. And then after that, we're going to have 2 oxygens to deal with, right? And both oxygens are equivalent. So we can't look at the trends anymore. In this case, you take the one that is the most acidic, and that one is the least. So the most basic one is more nucleophilic. So between this one and this one, we need to figure out which one is more acidic. Or which one is more acidic. So this one is more acidic. Why? Destiny, you're the only one left right now.
It's more acidic because it doesn't have resonance.
Wait, which one's more acidic?
Acidic would be the one with resonance.
Yes.
Right?
So
Yeah.
this one has resonance. So it's more acidic. And this one is more basic. Therefore, which one is going to be a better nucleophile?
The more basic one would be the better nucleophile.
Yes. So this one is going to go here. And then this one is going to be the least nucleophilic out of all of them. All right. That looks weird. Okay. Moving on, he has some other questions, which I think we went over, so I'm gonna skip those. But I think what it would be good is to go over question 14 on page 3 because I don't know if we got such a good chance to explain this, and it could be on your final. So in this question, he says that he puts it like this. He says A plus B equal a positive 15-degree spin, or specific rotation. And he says that B equals a positive 23. And this is asking about enantiomers. He says that A and B are enantiomers of each other. And so what percentage of A, so what is the percentage of A and what is the percentage of B inside of this solution? So if B is plus 23, and we know that enantiomers are exact opposites of each other, what's A? Destiny.
It's negative 23.
Yeah, negative 23. So if A is negative 23 and B is positive 23, how can we set this up? Do you remember how to do this?
Yeah, so I put it as like, I solve for A normally, I think. So I did,
Okay, let's write up the equation first. So
yeah,
it's A times what?
A times negative 23
Yeah,
plus,
A times negative 3 plus,
and then it would just be the 23. And then if you do like the x plus y equals 1, I just
Oh
like
wait,
flip that.
let's put this first to make it easier to
Oh, okay, okay.
understand. Yeah. So,
Yeah,
and what does
so,
this equal? What does all
oh,
of the rotations A and B equal?
positive 15.
15. Okay, good. So we set it up this way, and now go on to explain that part.
Oh,
What are
okay.
you going to substitute, your A or your B?
I'm gonna substitute for A, yeah, so I'm gonna solve for A. So I'll
You're going to
make
solve.
B, like I'll put B, like
Okay, so I can write
does that make
A plus,
sense?
yeah, so A plus B equals 1, and you're going to solve for B.
Yeah, yeah.
Okay. Uh, so, so basically here, the problem is that when we're looking at this equation, we have two variables. We have variable A, variable B. So all we're going to do is we're going to substitute one for the other using this equation right here at the top, right? Where A plus B equals 1. So
Yeah.
Destiny decided to solve for B. So B equals 1 minus A. So how do we incorporate this now? And I'm just going to
So
write
we,
everything.
yeah, we just rewrite it, and then for B, we would just put 1 minus A in parentheses.
Okay, cool. So we just took that B variable and we put it in terms of A, and that makes it easier to solve now. So what should I do now?
So I just distribute the 23 to like the 1 and then the A, and then rewrite.
Okay, so this would be a positive 23, right? And
Yep,
that would be a what? What would that be?
minus 23A.
Minus 23A. Yes. And that equals 15. So then we can just go ahead and start and continue solving. And what happens here?
Um, the
So
23. Yeah, because I'm just confused because that would mean 0, right? Is that I'm looking
Oh,
at my
wait.
work and I did it like a little bit differently.
Let me see.
Because the
Um,
23s cancel out here.
yeah. So
Okay.
the, oh wait, is that right? That seems wrong.
I don't know.
No, no,
That's
no.
why I did mine a little bit
Yeah.
differently.
So one of them, yeah. So two of them do cancel out, but then we're still left with another. Oh wait,
Okay.
no, no, no. Just a second. Wait. This isn't making sense.
Yeah,
How
I
is it?
think we made a math error.
Wait, I feel like they made a math error.
Yeah, because you're supposed to be able to add those to
Yeah.
get a bigger number. Maybe oh wait, no, it's supposed to be negative 23a because we dropped the a.
Wait, what? Oh, yeah. Oh my God. Yes, this is an A right here. That is
Yeah.
weird. Okay. Yeah. So it's negative 23, but there's an A there. So what happens here?
So then it'd be negative 46a plus 23
Negative
equals
40.
15.
Okay. Yes. So this is making sense now. So we combined this A with this A. So it was negative 23A minus 23A, so that makes negative 46A. And then that 23 is still left there and equals 15. Now we just have to go, and we're just going to do 15 minus 23. So I just brought this over onto the other side. Um, and that gives us negative 8. So negative 46A equals negative 8. And then A equals negative 8 over negative 46. What does that give us?
It ends up being a percentage of 17.4.
Okay, so what it looked like is 0.0174. And then that means it's, times 100. So the percentage of A is 17.4%. The percentage of B, okay, so if A is 17.4% of the solution, then the whole rest of the solution must be B because it's a solution where it's A and B. So you just take 100 minus 17.4, and that will give you um, 82.6%. So now that we know these two percentages, we're good because that's what the question was asking for. But there's another kind of question he can ask where he can say A equals 17.4. So we're just going to use the same numbers to kind of go through this, where he says A equals 17.4, um, B equals 82.6. What the enantiomeric excess? So his question is, what's the enantiomeric excess? So how do you find enantiomeric excess?
So you're just going to subtract. I think that you just subtract the larger number from the smaller number, right?
Or the other way around. Wait,
So just a minus b.
A minus B. Well, it would probably be B minus A,
Oh, okay. So yeah,
but it's similar. So you take 82.6 minus 17.4, and that should give you, I don't have a calculator on me.
I can do it.
Let
Did you get it? I have it.
Yes, 65.2. Did you get that?
Yeah.
So 65.2 is the enantiomeric excess. What that means is that 65.2% of B is extra over A. So 17.4% from A cancels out with another 17.4% from B. And this is the amount that actually influences the kind of like the rotation of the mixture. But you don't use all that. Just do this calculation, and that's the enantiomeric excess. Okay. Um, Next, he's asking about, wait, is that the same question that I just went over? Oh, this is the same page. Okay. Um, all right, so after that, there's just a few things that I want to bring up again. So just to remind you about like conjugation, like that's something really important to look out for. In organic chemistry, there's not he's never going to give you something where there's like two answers. I mean, unless it's like SN1, you have to give both the R and the S. That's like different. But he's never going to give you anything where it's like either way is fine. Like you should always look for which way is the absolute best because you might be getting it wrong if it looks like it's either way is fine. So this question, it looks like this. And essentially what's happening here is that, BR is going to protonate and then some base is going to come along, right? And so that base can help it's going to eliminate something, right? And so the question is it going to eliminate to the right side or to the left side? We could either eliminate here or we could eliminate here. Now the problem is that either way, there's no difference in terms of Zaitsev rule, which is the most important factor when you're doing elimination. You should always look for Zaitsev rule. And so when you're going to the right or the left, you look at that and you're like, okay, well, they'll both have two substituents either way, so it doesn't really matter. But really, you should stop yourself there and think there must be something else. And the answer is conjugation. So conjugation is really, really good and helps the stability of things. And so, um, therefore, and conjugation means that we have a double bond, a single bond, a double bond, a single bond, like that. So it has that pattern of repeating double bonds with a single bond in between. And so that means that the best option is for it to go to the right. Because if you draw it out, you'll see that nice conjugation right there. There's some conjugation right there, and that's great. All right. Then there's another cyclicization question that's really interesting. Check out all these questions here. They're all really good. But I think we should probably move on to, I'm thinking we should move on to the actual exam because I did go over this practice exam with everyone multiple times before the exam. So the rest of that just has some different like questions about like SN2 versus SN1 and like the different rates of stuff, racemic mixtures, and then there's some retrosynthesis. Um, so moving on to the actual exam from this year, um, which I haven't really looked at yet. Destiny, did anything stand out to you as like a little bit tricky compared to everything else?
Yeah, so actually, question number 3, I don't understand how you're supposed to know that it was going to give you like diastereomers.
Oh, okay, yes. So, with this question, it's actually really interesting. This is so I think in the video yesterday, I talked um, about ozonization versus epoxidation. And so, just as a little recap, they both deal with double bonds. But in ozonization, where you have O3 and then usually like H2O2 or something in the bottom, you're basically breaking that double bond in half, right? And I talked about that in the last video. But in this situation with epoxidation, epoxidation is going to be like this. Usually something like this. As long as you see this CO3H combination, it can be at the end of anything. It can be like a phenol that has a CO3H at the end of it. As long as you see this functional group at the end, and a double bond, it's going to be epoxidation, which means that you're going to form two things that you're going to form something that looks like this between the two sides of the double bond. You're also going to form the opposite of that. So what is this? This is a racemic mixture, all right? And it's a racemic mixture where you have the R versions and the S versions. Now, why are they diastereomers? Because in this question, this specific question, question number 3, he starts out, he has a chiral carbon on there. That's chiral to begin with. Now, this chiral carbon, Destiny, it's not going to change, right? Because that epoxidation interacts with the double bond, not the actual chiral carbon, right?
Yeah.
So, this is what he has as the starting point. and it's reacting with, CH3CO3H. And so what we're going to form is and I just want to change this into bond line a little bit. We're going to form the solid version, right? And on the other end, we have a solid, right? So it's going to form this, but also something very similar to it. The only difference is that we're going to have the 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 O's are going to be backwards instead of forwards. So when you look at this, since this one stayed the same for both of them, right? This went from, and you can do it out, but looking at the answer key, it just says this is R. So I'm going to take their word for it. This is R and that's R, right? And so since both of them are R and they stay the same, the other ones are changing though, because if you do it, this is 1. Like let's do this carbon right here. Let's do it in a different color though. This carbon right here, I'll do it in orange. The O is going to be 1, and then I think this would be 2, and then this would be 3. So you have to just treat it like a regular chirocarbon now. It's attached to an oxygen, a methyl, and an oxygen, a carbon, and another carbon. But the carbon on the right is attached to an oxygen, whereas the carbon on the left is attached to some other carbons. So that's why I numbered it 2. So if you do this, it's going clockwise, right? Clockwise with a backwards hydrogen. Clockwise, the backwards hydrogen is R, right? Let's do this one. So again, starting with this carbon right here. This is 1, this is 2, this is 3, and this is going clockwise, but it has a forward hydrogen, so it's going to be S. So already we've seen that this is a diastereomer. We don't need to continue to do the rest of them, because already from what we've seen, the chiral carbon all the way on the left has remained R, so that it went from R to R, whereas the second one went from R to S. So that tells us it's diastereomers. Okay.
Okay, that
Does
makes
that
sense.
answer the question?
Yeah, that makes sense. Thank
Okay,
you.
cool. No problem. Did anything else seem weird, or I see someone got this first one wrong on the answer key, so we can go through it maybe. All right, so they started off with a he gave us a cyclohexane, 2 cyclohexanes, a solid OH, and a solid CH2, CH3. And then for this other one, he has a backwards CH3 and a backwards OH. Okay, so the only thing we have to do here, so like we look at this whole thing, obviously it's not constitutional isomers. Everything looks great. The connectivity is the same. So let's just start by doing our R's and S's. So for this one, this is 1, this is 2, this is 3. That's going clockwise, backwards hydrogen. So that's R. Bottom one, bottom chirocarbon. I think this would be 1, this would be 2, this would be 3. So that's going counterclockwise, backwards hydrogen, that's S, right? Let's do this one. So, and again, in green, I'm going to do the OH in green again, okay? So in green, we have, this will be 1, this will be 2, this will be 3. So that's going clockwise with a forward hydrogen, so S, and wait, no, yes, S. And then following the same pattern in orange, I'm going to do a CH3. So this would be 1, this would be 2, this would be 3. Is all this adding up so far?
Yeah.
So counterclockwise with a forward hydrogen, that's R. Right? Okay. So yeah, so we see that the CH3 went from S to R, and that the OH, the chiral carbon with the OH on it, went from R to S. So these are enantiomers. Um, okay, I really like, because I used to find that so example from 2C. Does that sound good?
Yeah, sorry you cut out a little bit, but you said you want to do 2C.
Yeah, I
Okay.
like trying to do examples. Um, okay, so, oops. Um, Also, can you tell me if my internet gets bad again? Because it's been really bad today. Okay,
Yeah, I'll let
so,
you know.
alright, cool. So, actually, in this question, he didn't really ask whether it was meso. He didn't ask you to say whether they're meso or not. So the person, so you didn't really need to write meso. You could have just written identical as well. Because he didn't ask for that. But here we go. So if you do your so looking at this, there's a plane of symmetry, right? So that tells us something interesting. We go ahead to count. I think this would be one. So I'm gonna zoom in a little bit and look at each of these closely. Um, this would be um, one, two, three. That's going counterclockwise, backwards hydrogen, and that's an S. This other one is, again, it's going to have a similar situation where this is one, this is two, this is three. So that's going clockwise, and the hydrogen is back. So that's R. Let's do this one over here. This one is S. All right. So we see that basically there's an S and an S, and then an R and an R. So it's identical. But he didn't ask for whether it was meso or not. Now you know that this compound is meso. Why? Because meso has a few markers. Do you remember them, Destiny?
Yeah, so for it to be meso, it needs to be like an achiral compound or molecule. And
Achiral bond.
then
Mm-hmm.
yeah.
So the markers is that, yeah, it has to be achiral, but it has to have chiral carbons. So it
Yeah,
must
and then
have
another
those
thing.
chiral carbons. Huh?
And then I was just gonna say also like a plane of symmetry is that one.
Yes.
And then I think it was like optically inactive or
Yeah,
something like that.
inactive. Yeah. So I would take away this achiral definition because that doesn't really tell us much. But there's three things to look out for. It has to have a chiral carbons. It has to have a plane of symmetry, and it also has to be optically inactive, meaning that there has to be R's and S's involved. Okay. So you have to find both R's and S's in there. So if there's two chiral carbons, one has to be R, one has to be S. If they're both R, it's not meso. All right. Although this section isn't really important if you don't need to know this if you understand planes of symmetry really. Then you'll understand that that's not really important. But anyways, moving on. Um, let's go to see. Let's do the math question real quick because I feel like we could use more and more practice for that. So in this math question, he said, a he said a plus b, like all of it together, including the spins and everything, equals 20. And he says that b is negative 25. So this is just the same process as before. So I'm going to walk through it real quick. So I'm going to make b in red, and I'm going to make a in green. So all we have to do is put them all together. So a times 25 plus b times negative 25 is going to equal 20, this total right here. And so all we have to do is kind of substitute one for the other. So I'm going to go ahead, and this time I'll just substitute, I'll replace A with something from B, just to do like something that's opposite. So we know that A plus B equals 1. So A equals 1 minus B, right? So putting that in, A equals 1 minus B. So instead of A, I'm just going to write 1 minus B times 25 plus b times negative 25 equals 20. And then substituting this across, the 25 gets multiplied by the 1. So that's 1 times 25 is just 25. And then the 25 also gets multiplied by that negative b. So that becomes 25b. And then we have plus. Those just get multiplied by each other. So that will give you a negative, right? A negative 25b. So I'm just going to take out this plus sign and just write minus 25b equals 20. Now, from here, combine your b term. So combining this with this, we get negative 25b minus 25b. So that's going to give us negative 50b. And that is going to equal to 20. But I've also moved this all the way to the other side as well, minus 25. No. Uh, wait, what's wrong here?
At the beginning, I think that you're supposed to do like A to times 25 minus B, because I don't
Wait,
I
what?
don't know. Because it ended up being positive. My 50 was positive on my exam.
Hmm. Well, I mean, I don't think that matters that much because I think maybe you substituted B instead.
Like, because then my 25 was negative and I added it to the other side.
Yeah, that's what this answer key says, but um, how did that even happen?
Because I did 25A minus 25 times 1 minus A.
So you just substitute A, but it should work just as easily with B.
Yeah.
Um, let's just follow this through. Oh yeah, wait. No, that works out. No, that makes a lot of sense because um they substituted the other way around, so it works. Okay, so anyways, no, but it should work, I think. Uh, so 20 minus 25 is 5. So this is saying, let's just follow it through and see. So this would be 25, or that would be, sorry, just 5, negative 5 over negative 50, which equals just 10. Yeah, okay, 10. So it does work, yeah. It's not going to look exactly as the same as the answer key because I decided to substitute A for B instead of B for A. So B is 10%, right? And so now we know that B is equal to 10%. We know that A must be 90%. And that's that. In numeric excess, practice EE, would just be 90 minus 10, so it would be 80%. All right. Next, he goes on to all these different reactions. Here's one that looks like might have gotten wrong. Oh no, it's pretty much the same thing. So the one thing that I'm noticing here from so page 3, question 8E, when you do a triple bond, triple bonds actually look like this. Either side of them are flat. There's no like trans or cis with triple bonds, because there's no hydrogens involved to be the opposite way. So that's what he was correcting there. There's no trans and cis with triple bonds. The correct way to draw them is like this, and you guys will learn that in preparation for, so in the next portion, before the final, the new material you're learning is about triple bonds, and so that's something you'll have to be careful for then. So it's good to just know it now, that that's how triple bonds look. They don't really look like trans or cis or anything. They don't really have that stereochem to them. So let's go back up to the top. So this question, this first one, it looks really important, and that'll probably come up. He has a Br and then a Cl. So, and this is reacting with an NaCN. So you know that this is probably substitution, but you have to decide which one are you going to substitute onto. Are you going to substitute onto the Br or the Cl? Well, you have to decide which one is a better leaving group. So if you remember from your chart, Cl is a better leaving group, right? Because it goes, wait, is it?
No, I think BR is a better leaving group,
BR is a better
but
leaving group.
well, this
Oh,
is
no, no.
because
The
of the
problem here is
stability.
that, yeah. So, there's no, so Cl is a better leaving group. Sorry, Br is a better leaving group, but we're not going to be doing the substitution when, what do you call it? I think it's because there's a double bond right next to it. Right. Has to do with this double bond. Did you get this right, Destiny?
Yeah, I took off the Cl just because it has like not as many double bonds near it, and I
Yeah.
remember learning that.
Yeah. So basically this double bond is problematic because it's very hard to leave if you already have double bonds there. And also, everything that we've learned about SN1 and SN2, there's no double bonds involved. Like you don't have like, if you have a double bond already here, you don't like protonate the Br and react it like normal. That doesn't work. Like you can't do this. You don't really attack like double bonds. Everything we've learned about substitution is that it doesn't attack near double bonds. Usually there will be no double bond there, and that's fine. So that's why this one is off limits. This one right here. So I probably shouldn't have drawn it this way. I'll just draw the double bonds in. But it's important to know, because even if he does draw it this way, it's important to know that you're looking at double bonds there. And so you can't do substitution with this one. There are ways to do substitution with this one, but you're going to learn that in Orgo 2. Okay. So, but it's completely different. It's a completely different reaction. Plain substitution can only happen with Cl here. So we're going to just substitute the Cn into that section where the Cl had been. And again, just like one little tip, like you could get points off for this. Don't ever show it like your nitrogen is attached to there. So don't do like Cn that way with your N closer to the thing. It's always the carbon that's attached to the actual other carbon. Okay. Because it's C and the minus is from the C, not the N. So it's the carbon that attacked it. Substitution, okay, elimination. Let's try this one. So with TSCL, so I'm gonna go through D right now. So we've got this. And so this is reacting with TSCL, purity, and DMF. but it also has Na and 3. So it's one TSCl. And if you write these numbers, it means that first you react it with the entire thing on top, then you throw in this other thing, if you write the numbers. So TSCl, and then the bottom one is Na and 3. And so from what we know with TSCl is that it's a good way to start protonating an OH. So if you want to protonate an OH, it's always good to use TSCl, because what happens is that you can form this, the same thing, but instead it's OTS now. And then with the Na and 3, the N3 is just going to come attack that like a nucleophile. So we got that. And it's important to make sure that your stereochemistry changed. So I just changed it from down to up. But then I would recommend just checking real quick whether this is actually changed. So this is R and this is S. So we're good. The next example also has TSCl, but in this case, it's already attached to the thing. So this is actually really interesting because it doesn't look like the way it is, but basically, so basically we start out with, this is the one that I was talking about the triple bond. So we start out with this, and also a phenol that is already in the form of OTS. So this is important because people might think, but you need to recognize that this is already the leaving group. So the leaving group is this from the O. So it's going to protonate off, breaking off from the CH2CH3. And then the nucleophile, which is this carbon over here, is going to attack this carbon. So what you get is first let's draw those two. So I'll just draw them two in bond line structure form. So there's two carbons, and they are attached to a C that is triple bond attached to another C that is like that. But I also don't have to write this part right here. Yeah. No. So this is how it looks correct. So basically we just have this portion from right here, and then we have the triple bond that has attached onto it from the nucleophile. And again, like if you want to draw it correctly, with triple bonds, you don't have this like stereochemistry. There's no cis and trans for triple bonds. It's just all flat. The next one is exactly what we were looking at. It is basically which one is a better leaving group. So in this case, you just have a Br and a Cl. There's no double bonds involved here, so it's protonate the better leaving group, which is Br. And then use that for the elimination. Again, as soon as you see an SN1, you have to do a racemic mixture. That's for G. So you need to do one where the hydrogen is forward, one where the hydrogen is backward, essentially. And the rest of it has to look exactly the same. And then what else do we have? Okay, that's not too bad. Let's do this one. So this is question I. So there's two chiral carbons here, it looks like. So what do we see here? What do we recognize from this, Destiny? The part that I'm writing right now.
That's a good leaving group.
Exactly. It is OTS. Right? So we're reacting this with NaCN. So the most important part here is to identify the good leaving group. So you have two leaving groups, right? You have OTS and you have Cl. So either this could protonate or this could protonate. But you need to be able to remember which one's a better leaving group, and it's going to be it's going to be this one is a better leaving group. So we protonate that. So our answer is going to look exactly the same in every other way. But we sure that there was, inversion there. And so the CN is going to go on this side. And the reason why he did something in red there is because he was saying you can't, it's not like the nitrogen attacks the carbon. It's in CN, it's in NaCN, it's the carbon that attacks. The carbon is the nucleophile part, not the nitrogen. Okay, so he has another question here, which we already went through, about figuring out A pathway, B pathway, then identifying A, B, C, and D. That stuff we already know. But let's go back to question 10, because question 10 has some other stuff in it. Let's do a cyclicization one. And this is reacting with CH3O minus. So what do we know about CH3O minus? It's a strong base, right? But here he said it's cyclicization. So you might be tempted to say, oh, this is going to be elimination. No, because he said cyclicization. You know that, as I said, cyclicization is always substitution. So that means that you're going to be doing a substitution instead. So what's going to happen is that this O minus is more likely going to attack this hydrogen as well. It's going to be involved in attacking that hydrogen. Probably in real life, you're going to get a mixture of both elimination and cyclicization, but he wants you to show the cyclized product. So you might get two products, one that's eliminated and one that's cyclized, but he wants you to show the cyclized product. So basically, let's just figure out our carbons again. So the carbons that would be involved are everything in between the leaving group and the nucleophile. The rest of these are not going to be involved in the actual circle. They're going to be hanging off the circle. So that is 4 carbons are going to be involved. So this and these 3 are going to be hanging off the circle, not really in the cyclized part. So if I just draw those 4, right, we've got 4 carbons. And the one on the left has a Br on it, and it also has an ethyl. Br is going to be protonating, right? And the carbon on the right, all the way on the right, has a sulfur with a hydrogen. And also in between that, let's not forget about this, there is a methyl hanging off of this one. So what's happening here is that the lone pairs from the sulfur are going to be attacking this carbon where the bromine is attached to. And so one thing that I said, like a tip for making your cyclized things look nice, like we have 1, 2, 3, and 4 carbons involved. That means we're going to have a 5-membered ring. So you can just start drawing like a 5-membered ring. And then put your sulfur in one of those places. So then we just need to figure out like how everything else is attached. So let's go to 1 over. That one's going to have the ethyl on it. And then also on this other carbon, we're going to have a to make sure about is stereochemistry. So initially, this carbon that has been attacked by the sulfur, it's undergoing a substitution, right? It's undergoing SN2. So when it's undergoing SN2, we know that we need to change it from R to S. So let's do initially how it was. Was it R or S? So this would be 1, this would be 2, this would be 3. So that is going clockwise, and there's a backward hydrogen, forward hydrogen, so it's S. So this went from S, and now we need to make sure that it changed to R. Now this is the tricky part. So again, we're talking about this carbon right here. It needs to have changed to R. So this is going to be 1. The way that I recommend doing this is counting and then deciding which way you want to put your hydrogens. So that would be 1, this would be 2, and this would be 3. So this is going in a counterclockwise direction. And we need this to be R. How do you get counterclockwise to be R? Does the hydrogen have to be forward or backwards?
It has to be backwards. Wait,
Backwards.
no, sorry,
No,
forward.
forwards. So then I'll just draw a forward-looking hydrogen, like this. And since something is forward, we need to make something backwards. So the key to this is that you could make any one of the other things backwards. It doesn't matter which one. So one of the options is to make this one backwards, which most people would choose that. But it also really doesn't matter. You could just go like this and make that backwards. It's fine. Just one of them has to be backwards. You could also do this other one as backwards. As long as one of them's backwards, you've got the right answer. Hydrogen, the most important part though is that hydrogen is forward. Okay. So then what else do we have? Another substitution question. Rearrangement. Okay, this is interesting. He said rearrangement. So let's do this one. We're starting out with a cyclopentane, and it has an OH, 2 methyls, and this is reacting with H3O plus. And he says that there's rearrangement here. He didn't ask for the mechanism or anything, but he says that there's rearrangement. So if we envision what happens, right? First, it would help to know the mechanism. The lone pair from here comes out, attacks that hydrogen. This goes onto here. So then we're left with this pentane, but there's an H2O on it. H2O is a good leaving group, so it's going to leave. And what we get is we're going to get a carbocation. Now, this is the part where the rearrangement might happen. Carbocations like to rearrange if there's a possible better place for it that's more stable. So what's going to happen is that this is going to shift over. One of these methyls is going to shift over. And so that's going to create a situation that the methyl moved up and the plus charge is now there. And so then elimination is going to happen from that chiral carbon. And so I'm going to redraw this so we can look at this better in a bigger picture. But where are the possible places that we could cause elimination to happen?
It would be like to the right or to the left of like the plus sign, right?
Mm-hmm. There's another option.
And like up, I mean, too. Sorry.
Yeah.
Like above it.
Yeah.
Yeah.
So there's 3 options. There's 3 beta hydrogens, 3 possible eliminations. We could form a double bond going this way, or this way. If you do them all out, you'll see that one of them is much more advantageous because it follows Zaitzev's rule. So it's going to be this. The double bond's going to form here, where it has 4 substituents, because that's the most favorable. Okay, some other random stuff. Which of the following statements is false? That's interesting. Okay, I wouldn't have expected that one. So let's examine this. So racemic mixtures are optically inactive. Well, racemic mixtures contain both R's and S's, right? Which makes them, yes, optically inactive. Optically inactive is R and S. And then if you have just R, or like way more of R, that would be considered active, optically active. Meso compounds contain equal amounts of enantiomers. So meso compounds don't have enantiomers really. As soon as you try to make them into enantiomers, they're just identical. So there's no way to make a meso compound have enantiomers. And you can try to draw our fun little meso compound. So maybe usually a meso compound will look something like this. So the markers of meso, it has a plane of symmetry, has two chirocarbons. One is R, one is S. 1, 2, 3. This is S, this is R. So yeah. So it contains all the markers of meso. Plane of symmetry, check. Chiral carbons, check. And optically inactive, check, right? So basically this is a meso compound, and you can try to create enantiomers for it, but you won't be able to, because let's just take it, right? And let's try to create enantiomers now. So enantiomer means that everything has changed, right? And this is the classic one that I keep talking about because I don't want, anyone to mess up on it, and people do really well with this. If you try to create an enantiomer for it, so we changed this one that had been S to R, and we changed the ones that had been R to S. Oh, sorry. We see that it just went from, like, there's no way to tell, like, this is the same carbon right here, and this one is the same carbon right here. So these are identical. So you cannot create enantiomers with meso compounds. Is this making sense? Because they're
Yeah.
just the same. Okay. We have 5 minutes left, so let's just come straight back because it's nearly 6. And then so that's why that one's false, because you can't create enantiomers. Enantiomers have specific rotations which are equal but have opposite signs. From doing those math problems, we know that this is true. Like, enantiomers are complete opposites of each other. So if one enantiomer has a rotation of plus 60, the other enantiomer is negative 60. Achiral molecules are optically inactive. So if chiral molecule is optically inactive, it's usually meso. Um, so yes, that's true. They are optically inactive. Meso and so meso compounds, this is something I just want to clarify. Meso compounds are achiral. You can have some things that are achiral but not meso. For example, this compound right here. This compound is what? Achiral. Why is it not meso? And also, why is it achiral?
Can you actually go over that?
Okay, so first off, is it chiral or achiral?
Um, it's achiral because it doesn't have, they're just not chiral carbons because of the double bond, right?
Right, yes, there's no chiral carbons there. So this is achiral. But it's not meso, because in meso we need to have a chiral carbon, we have to have a plane of symmetry, blah blah blah. There's no like chiral carbons here to make it meso, right? So it's achiral, but not meso. Now here's another example. Let's just take the example from right above. This one is also achiral, but it is also meso, because it's achiral because chiral carbons are kind of like the opposite of meso. They have to have chiral carbons in them, but they also can't have a plane of symmetry. So an example of something that's chiral would be this. This is chiral. All right. So here we've outlined all the 3 different possibilities. There's chiral compounds, achiral and meso, and achiral but not meso. All right. So does that clarify kind of? Achiral is like this umbrella term, and it involves both meso things and things that are not meso.
Yeah, that makes sense. Thank you.
Okay. So the definition of chiral, though, is that you can't have chiral and meso. If it's meso, it's definitely achiral. So why was I saying all this? Uh, achiral molecules are optically inactive. Um, so that is true because in this case it's optically inactive, or like in this case there's no chiral carbons, so they're optically inactive. Um, because having no chiral carbons will make it inactive.
Yeah.
Having no chiral carbons, you're not going to, right? And then this other thing about pentacoordinated, I know I brought it up before, but just like one more time. So like when we know what we know about like um SN2 is that let's say that there was gonna be like N3 substituting onto here. This happens at the same time as bromine is kind of leaving. So what we have is we have a carbon that's attached to two other methyls, whatever. And there's also hydrogen here that a lot of people forget about. Um, but in terms of these other ones, it'll be kind of attaching to the N3 at the same time as it's disattaching from the Br. So this creates this 1, 2, 3, 4, 5 pentacoordinated state. Just for a split second, but it is there. The state where the carbon is possibly attached to 5 things at the same time, kind of. So that's like, what do you call it? What pentacoordinated means. And then one step meaning that all of this happens in one step. There's no like carbocation intermediates. Um, anything else? Okay. So I say about what we were just talking about. Like it's really important to know this stuff right here, because it'll kind of just help you with understanding everything. And if he throws any of those questions at you about understanding stuff, you'll know it right away. The difference between achiral that's meso versus achiral that's not meso, and then how that differs from chiral. One thing though that I really want to bring up because I feel like a lot of people might get this wrong. This right here, is this chiral or achiral?
Um, that would be a chiral because there's no chiral carbons, right?
There are chiral carbons. Yeah, there's 2 of them. Um,
Oh, okay. Yeah, yeah, I see now. My bad. Um, honestly, I don't know.
okay, so this one, people might be tempted to say that it's meso, right? Which means achiral. So what are some of the things that might make you think it's meso?
Um, kind of like there being like a plane of symmetry.
Plane of symmetry. Okay. And then the fact that there's chiral carbons.
Yeah,
So,
and then it's probably R and S, right?
well,
I
check
didn't.
that out.
Yeah. Okay, let me look. Okay, so no, they're both S, so
They're both S.
that's what I got. So that would be not, that wouldn't be
So,
meso because,
yeah. Is it optically inactive? No. It's optically active because it has only S's. So, basically, like, one thing that I would point out about this is that plane of symmetry, there isn't even really a plane of symmetry here. Because this bromine is going backwards, whereas this bromine is coming forwards. You see that?
yeah.
That's not even really a plane of symmetry. Also, also, S's and S's cannot be mirror images of each other because they're exactly the same thing. They're not mirror images of each other. They're not superimposable. So this is not. So this is an example where you might be tempted to say meso, but it's really what? What would you call that?
Um, oh, it would just be, wait, I don't know.
So the options are chiral, achiral, not meso, achiral, meso. There's
Um,
literally only three options.
so it'd be achiral then?
No, it's not achiral because it has chiral carbons and everything.
Oh, okay, so chiral then.
It would just be your standard chiral, yeah.
Okay.
So go over that one and examine why it ends up being chiral. And then compare it to all these other ones. All right. What else do we have? Um, so from what I'm understanding, if you see a plane of, so this is the question where he asks you how many diastereomers are there possible. So if you see a plane of symmetry, then you can, when do you subtract one? You subtract one if it's meso, right?
Yeah.
So in this example right here, because people are confused about when do you subtract one versus when do you not subtract one. And I think in the beginning of the semester we thought something completely wrong. So, so the first thing you have to figure out is how many chiral carbons are there. And there's only two chiral carbons. There's one here and one here. So you take 2 to the n, and n is the number of chiral carbons. So that would be 2 to the 2. And in this case, we're going to subtract 1 because it's a meso compound. Um, if you look at it and you go through it, like first of all, we see a plane of symmetry there. We see that there's more than one chiral, that there's definitely a chiral carbon there. This would be 1, this would be 2, this would be 3. So that's going clockwise, and there's a forward hydrogen, so that's S. And then this is 1, 2, 3, and it's going counterclockwise. It's going counterclockwise to forward hydrogen, so it's R. So it's R versus S. So this checks all the markers for being meso. So since it's meso, you have to subtract 1. And then that gives you 3 diastereomers. Again, if you had said enantiomers, you would say there's no enantiomers for a meso compound. But for diastereomers, there is. So if you said, how many enantiomers are there of this? You would say 0. Said diastereomers, you would say 3. Okay. So this is for meso compounds. And then the next one is just a standard diastereomer. It's not meso, so you don't need to worry about that. All right, what else do we have? Can this molecule be described as meso? Yeah, this seems like it might be the hardest thing on the final from this exam, meso and stuff, because it's hard to understand this stuff well. So he has these compounds right here, this compound right here, and he says, is it meso? So when you look at it, what are the markers of meso? The markers are that it has a chiral carbon. It has a plane of symmetry, and it's inactive. All right. So let's like put this into a chair or like into a regular drawing and see. So we've got a cyclohexane and we've got two methyls. One is they're both going down, right? This is going down, this is also going down. So we have two down methyls. So I'm just going to draw them like this. And then we have, this is 1, 2, 3, 4. So on the fourth carbon away, we have another one. So this is 1, 2, 3, 4. So there's one down here. Is there a chiral carbon?
No, they're both achiral carbons.
Exactly. So right off the bat, nah, that's and you can say that. You can just say, nope, this is not meso because there are no chirocarbons. I think that would be enough of an explanation, personally. Not chiral and not meso because there are no chirocarbons. Um, is there plane of symmetry? Yes, but that doesn't matter because there's no chirocarbons. Is it inactive? Um, I think it's inactive. Well, there's no chirocarbon, so there's no way to determine if it's inactive. Yeah, because you can't assign RNS. But actually, no, sorry. Remember I said that? I said inactive is if you have no chirocarbons, that's also inactive. So essentially, the reason that's not meso is because there's no chirocarbons. If you made this chiral somehow, then it would be. Um, but anyways, what did I want to say about this? Hmm. Yeah, I guess that's it. I don't know. Did you do you get this one?
Yeah, that one makes sense.
Okay, cool. All right. Now we're on page 7, and we've got 8 minutes left. So, do you see anything here that you think would be worth talking about? Anything that needs to be talked about, or should I do some
Um,
retrosynthesis or what?
I kind of wanted to go over, like, if we have time, maybe we can go over the bonuses, because I thought that
Okay.
page was pretty easy.
Okay, let's go over the bonus. Yeah. So, should we start with what you want to start with? That retrosynthesis looks a little long, so maybe we could talk about that. We could also talk about there's 2 retrosynthesis, and then there's a. Oh, okay. You want to do the first one?
Yeah, we should do that one.
Okay. So he says there's a 1 bromo, 2 dimethyl propane, and it has difficulty undergoing either SN1 or SN2. Oh, why does it have difficulty undergoing either SN1 or SN2 reactions? So let's draw this out. So it's a propane. So it's gonna look like that. And there is the first carbon has a bromo on it. Then the first carbon also has a methyl. The second carbon has a methyl. Why is? Oh no, I wrote it wrong. This is 2, 2, 2. So it looks like this. All right. So why does this have difficulty undergoing SN1 or SN2? So this is what are we looking at? It's a primary leaving group, right? Primary leaving groups, they always undergo SN1 or SN2, right? Yeah. So it
Yeah.
has difficulty undergoing SN1 because it is primary, right?
Mm-hmm.
Because of primary.
Oh, okay, so basically you just wanted us to recognize that it's primary, and so it's more favorable to go under SN2, basically.
Well,
Right.
it also has issues. He said, why does it have difficulty undergoing either SN1 or SN2? I think he means both SN1 and SN2.
Oh, okay.
So there's issues also undergoing SN2. Why? If you look at this whole area is very like bogged up. And SN2 involves something attacking from behind, right? So that means that maybe let's say we had a nucleophile N3, this would have to come in from behind, right? But it's very hard for N3 to come in from behind because of all this stereo hindrance, this involvement of other branches on there. So it has to go through a whole bunch of other stuff involving like hydrogens, carbons, all that kind of stuff in order to get to that backside attack. So it's very unlikely to do either, basically.
Okay.
Also unlikely to go to elimination because there's no beta hydrogen. So this is very just an unlucky molecule. And we talked about stereohindrance and how it affects things a little bit. It's like if you think about a really bulky molecule, it has a hard time doing different things. So sometimes if you have bulk on one side, like if you have a BR, um, but like it has like a lot of bulk on one side, it'll prefer to just do elimination to this side because it's hard to do elimination towards the bulk. So think of hindrance like bulk. If you see like like a bulky molecule, then you know it's going to have issues doing certain things from certain directions.
Okay, that makes sense.
Um, so let's go through this retrosynthesis. Which one do you want to go through? The top or the bottom?
Can we do B? I don't really understand B, but C, I just got stuck on one part, but I think I get it after looking at the key.
Oh, okay, okay. This is interesting. All right. So this one, I remember this actually. This one is such a good one. So basically, what's the difference between our starting and ending?
There's an addition of a double bond in the oxygen.
Okay, but also something else happened. We lost a
Um,
carbon. I always say to count your carbons first, right? So it's three, four,
oh
five,
yeah.
6. So there's 6 carbons here. And there's 1, 2, 3, 4, 5. And remember what I said, at this stage, we only know one way of losing carbons. One way, and that is ozonization, right?
Hmm.
We have one way also of adding carbons. We know of one way of adding carbons and one way of taking away carbons. So if you need to take away a carbon, and use this tip wisely because in Orgo 2 it all changes. There's so many ways of adding and taking away carbons. Take away a carbon, then it means ozonization. If you add a carbon, that means that you did CN, a substitution with CN. Okay? So those are
Okay.
the only 2 ways we know of doing this now. So we know that a carbon left and there's a double bond O there. That's just like, telling you ozonization. It's just screaming ozonization, right?
Hmm.
So we can just start from here and let's just make a double bond. What do you want to do? How
Um,
can we create that double bond to do ozonization?
okay. Um, well,
Wait, can
double
you hear me?
bond? Yeah.
Okay, cool.
Can you
Yeah.
hear me? Okay. Um,
So we're gonna try to figure out a way to make a double bond to do ozonization. Would be to try to create. I mean, we could start from the other side as well. Where do you want to start from? The right or the left?
I think I'd rather start from the right side,
Okay.
because
All right. So
then
yeah,
we just
that's the
know
way you're supposed to
exactly
do
what
it.
to do. Okay.
Yeah. Okay. So let's just do this. So what do you think we had right before that last step?
Um, Probably, well, we'd have a double bond because we had to do the ozonal, I don't know how to say that word, but
Yeah.
yeah, just a double bond. So then before that, we would have had to create the double bond,
Mm-hmm.
which you can just do that from, like, can you do that from a hindered base, or should we do something different? Because would this be like the hindered base open space thing?
It's kind of, but also not really, because um, I personally think oh yes, 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 because here I think this might be the reason that he put it as a bonus question instead. So if we had let's say we had a CL here, right? We
Hmm.
have the option to do 2 different eliminations. We could do an elimination towards the top with this hydrogen, or we could do an elimination towards there. Obviously, it would favor this, but the open space thing,
Yeah, so okay, so for that reason, we would do a hindered base.
a hindered base. And
And then
then,
before that,
mhm,
like, you would just need to do for that one, you would do like or no, Cl2 and like light, right?
Yes. That's it.
Oh, okay.
I think the
Yeah, I
trick
think
here,
I could.
a couple of tricks. The first part is that he removed a carbon, and it's hard to know that. And the second trick is the fact that you have to use a hindered base.
Yeah, I think I got stuck at the hindered base part. I didn't really
Yeah.
remember it.
But my tip would be if you're doing a retrosynthesis and you're like, oh, this is a minor product, I can't figure out how to make it a major product, just go ahead with it. He'll give you most of the points, maybe not even take off any at all. Because,
Hmm.
and you can write a note like, this is a minor product, but it's still a product, so.
Yeah.
All right, cool. Do you want to do that last one or no?
I think I'm good on that one. I just put the double bond in the wrong spot, so I didn't get my product in the right spot.
Yes.
I don't know why. I completely forgot that I could put it the other way.
Right, yeah. Okay,
So,
cool. All right. I think that'll be the end of our session then today.
okay,
Um,
thank you.
thank you